Limits are a useful tool that we'll be using in order to study derivatives. The idea of a limit is to study how a function behaves near a point, but without looking at what the function actually does at that point. So you might be wondering why we care. Before I give you the mathematical reason, let's imagine the following scenario. So let's suppose that there was a recent earthquake which caused a fissure to open in the side of a hill, and you want to determine where that fissure occurred. Well, you can determine where it occurs by walking right up to the edge. However, if you try to determine where it occurs by standing on top of it, then you fall to your doom. Now, when we study derivatives, something similar is going to happen. We'll be given a function that has a hole in it, and we'll want to look at what the y value is of that hole. Now, to do this, we'll walk right up to the hole, but without stepping on top of it, which we can't do because the function's not defined there. So let's define a limit. Suppose that f is a function which is defined in an open interval of a point c. And here we use an open interval just to ensure that we can actually approach c from either side. Now we say that the limit as x approaches c of f of x is L if f of x gets arbitrarily close to L as x gets arbitrarily close to c. Now the words arbitrarily close here are important. If you were to take an advanced course in calculus, turning that phrase into mathematics is actually a hard and arduous task. But luckily for us, we're not going to worry about that, and much of what we'll be doing is hand-waving in order to find our limits. Now as our first example, let's look at the function x squared plus x as x approaches 2. This function is pretty nicely behaved. Right? It doesn't have any holes like I mentioned above, but let's start with nice functions before we get to the ugly functions. So for this problem, and this problem only, I'm going to make a table of values. And I want to say that this is generally a terrible way of computing limits, and you are absolutely not allowed to do this, but because this is our first exposure to limits, we'll go through the motions. So I'm going to plug in numbers which are very close but not equal to the number 2, and see what values our functions give out. What we're looking for here is whether f of x is getting close to one number in particular. If we stare at our table long enough, yeah, it looks like it's getting close to the number 6, so that's what we'll set the limit to be. So hopefully you've noticed that if we had just plugged x equals 2 into our function, we would have gotten 6 out anyway. And again, this is because the function is well behaved at x equals 2, right? It doesn't have any holes or weird jumps. And this is going to be the general rule hereafter. If the function doesn't do anything weird at the point you're looking at, then you can evaluate the limit by directly substituting the number into the function. We're going to learn the proper word for this. It's called continuity, but that's going to be a little bit later on. Now in the table above, you'll notice that I never looked at what happened when x was equal to 2. And generally when we take a limit as x approaches c, we always demand that x is not equal to c. This is actually very useful, and we can use it to help us solve limits. To see what I mean, let's take a look at the following example. Now we've run into a problem because this function actually does weird stuff at the point x equals 4. Right? To see this, if you plug x equals 4 into the numerator and work out the math, well, you get an answer of 0 out. Plugging x equals 4 into the denominator, well, that also gives you 0. So this function behaves like 0 over 0, which is just, total nonsense, and we can't determine what's happening the way it's currently written. However, if we factor the numerator into two linear terms, one of these will cancel the linear term in the denominator, giving us a form which is much simpler and is well behaved near x equals 4. But I have to emphasize that this last equal sign is only true because we've said that x can't be equal to negative 4. All right, so if we throw this then back into our limit expression, we can work it out. And doing this gives us x equals 12. All right, let's do a harder example. Okay, so let's look now at this following monster of a function. Like the previous example, this function is badly behaved near x equals 13. And you can check that if you plug x equals 13, both the numerator and the denominator evaluate to 0. But an old trick from high school is to deal with the square root by multiplying by the conjugate. Remember that the conjugate looks like the square root term, but with the intermediate sign switched. And we do this because it allows us to take advantage of the difference of squares formula. So look at what happens. The numerator simplifies to a linear term which cancels out the denominator. And again here, of course, we're assuming that x is not equal to 13. This new form is well behaved near x equals 13, so we can plug it into our limit and evaluate to get out the answer, which we find is 1/8. Okay, so generally what have we learned? Well, we've learned that we're going to need to manipulate, or sometimes we need to manipulate a function in order to determine the value of its limit.